Good morning, my fellow scientists. It is Wednesday, April 19th, 2017, and I want to talk to you a little more about the iron battery. I noticed something yesterday when I was working with my all-iron cup cell that it seemed like there were little bubbles forming on the iron wire. Now, zinc is well known for producing hydrogen gas when it is immersed in hydrochloric acid. Iron has the thermodynamic potential to do so, but is much slower. So the reaction I'm worried about is iron plus hydrochloric acid, which dissociates to H plus and Cl minus in solution, will go to iron chloride, FeCl2, plus hydrogen gas. So the thermodynamics for this are definitely favorable. So for those of you who've gone through freshman chemistry, this is a negative delta G reaction. This guy's going to be soluble, but I thought the rate of this reaction was going to be super slow, but yeah, definitely not as slow as I'd hoped. So I actually saw bubbles, and so today I tested that to see just how fast it was. And here's the time lapse. You can see this is about 20 minutes of real time, and afterward, yeah, there's definitely some hydrogen gassing going on. So the way to suppress that is either to use a better electrode material, something that has iron adsorbed but suppresses hydrogen production, for instance, or better to go to a alkaline solution. So you want to go to something like potassium hydroxide. That's how the Edison cell works. This is the well-known 1901 Edison cell. That uses an iron-nickel chemistry. Nickel is relatively expensive on the scales I'm thinking about, so I don't want to use the iron-nickel chemistry. I want to use all iron chemistry, but I would like to go to the alkaline pH so that hydrogen production would be suppressed. Here's the trouble. It's not as easy to keep the iron cathode stable in a alkaline solution. So iron metal goes to iron hydroxide. That works. That's the same as the Edison cell. Iron something has to go to something else in order to take up those electrons at the cathode. So I'm not going to balance my equations. I'm just going to make this simple. But if you have iron and hydroxide, so iron in an alkaline solution, then you can make iron hydroxide. That's what happens in the Edison cell, and that liberates some electrons. Now, if that's the case, you have to have something that takes up those electrons and becomes something else. The question is, what? What do we use to take up those electrons at the cathode? Now, my first thought was, let's use magnetite, Fe3O4. That can be reduced from Fe2O3, or iron oxide, or basically just rust. But I can't find anything in the literature that refers to this reaction. That's usually not a good sign. I'm hopeful that the performance will be decent on a dollar-for-dollar basis, but let me just caution you all that on a battery weight or size basis, this battery is not going to be any good, right? So commercial chemistries like lead-acid batteries or lithium-ion batteries, all of these have cell potentials on the order of 2 volts, and they can pack a lot of material into a smallish battery. So they're going to win, unquestionably, on capacity, on performance. But lithium, nickel, lead are all relatively expensive and, in some cases, toxic relative to iron. So that's the only advantage to this chemistry. It's not going to be in performance. It's only going to be in price. And maybe accessibility to students who would like to play with this and build one for an education or other science projects. So anyway, stay tuned. I hope that's interesting. We'll talk more tomorrow about chemistry and batteries and iron here in the Allen Lab.